Okay, welcome back, everyone. So I hope you have a very refreshing break. So now comes to our next session, section 3, so accountability and transparency. So I would like to introduce our next speaker, Dr. Ilizon Demotra. And Ilizon is an associate professor of applied mathematics and also computer science at Imperial College. So he's also a special advisor on AI and data protection to the EU Commission's and Justice Commissioner Reinders and a Parliament-appointed expert to the Belgian Data Protection Agency. So his presentation today would be detecting the use of copyright protecting content by large language models. So please join me in welcoming Ilizon and hand it over to you.
Perfect. Okay, so I think, okay, perfect, it's working. Cool. We actually have like a reasonably sized audience. I basically have, I think, 45 minutes of content, but this is really meant to generate questions, interactions. So please feel free to interrupt. I think I have 3 big, type of methods, and maybe after each type of method, after telling you what I think are the pros and cons of each of the methods, I can pause and we can take questions. So I really want this to be interactive as opposed to me speaking for 45 minutes straight. So today I'm going to tell you about how do we detect the use of copyrighted content by LLMs, and also how some of those methods might tell us something about how LLM learn and memorize. So as you all have seen, right, large language models are like, changing the world. This is my slide on how it's going to have such a deep impact, right? We don't know exactly where, we don't know exactly what the product is, but I think what we all can agree on is they will have a massive impact across the board. However, every time we talk about reasoning and intelligence, and every time we try to anthropomorphize a little bit those models and try to project some capabilities, some human capabilities onto those models, it's all too easy to forget where the actual intelligence comes from. And like every machine learning model before, the intelligence comes from the data. We have really, really smart ways of learning, really, really smart ways of remembering and learning and generalizing. The algorithms are increasingly sophisticated. We have a bag of tricks on how do we get LLMs to actually learn efficiently and behave and talk in a way that makes sense to us. But fundamentally, the intelligence, both the ability to basically write and what it knows, comes from training data. All of those models, modern models, are trained on crazily large amount of data. GPT-3 was 300 billion tokens. The DeepMind one was 1.4 trillion GLAM, so the one that came before Gemini, 1.6 trillion tokens. At the beginning of times, a year ago, everyone was very, very excited to tell you how they train and where the content comes from. Most people were actually relying on openly available data sets like Command Crawl. However, things have increasingly changed. Competition is increasing, valuations are increasing, and people are increasingly keeping the content secret. What they actually train the model on is increasingly seen as the secret sauce. We have a sense of where some of it might come from. This is what's in the one of the data set. I think this is Command Crawl. And then you can see that a lot of it comes from Patent, Wikipedia, and then basically a lot of newspapers. And the question that we're going to try to ask here is, some of this includes both copyrighted and harmful content. can we try to understand where the intelligence comes from? Can we try to understand where the facts are coming from? Can we try to understand the way it writes by understanding the training data and what is available to us to understand how these models have been trained and more specifically on which kind of data? Can we audit them? There's basically, and this is fast evolving literature, there's basically three big type of methods. The first one, earlier, the first method, this is 2003, provenance. Basically, most models were trained on command crawl. Command crawl is openly available to anyone. Can we develop tools to basically efficiently understand what is in those hundreds of gigabytes, hundreds of terabytes of data? Where does this data come from? There are a bunch of tools looking at the pile is a big data set, Rick Pajama is another one, C4 is another one, and basically a bunch of tools, in particular two of them, What's in My Big Data by the Allen Institute and the Data Provenance Explorer by MIT Media Labs were the first tool to basically try to understand what have those models seen during training, and whatever they know in the way they write and whatever bias they might include and whatever copyright content they might have seen, can we try to understand what went into those models? So we talked about, unfortunately though, is that companies, this was the good old days in a sense last year, companies were very open. We use command crawl, we use this one, we use C4, we use MC4 English, et cetera, et cetera. Now all the companies are closing up. This is an index from Stanford on openness and transparency of foundation models, and you can see that a lot of them are scoring quite low. Even Llama, which is an open model, only scores at 54%. Specifically, they decided, Facebook, it's one of the most open companies, they decided to stop publicizing what they use to train their model. You have this Arthur Mensch, right? He's one of the co-founder of Mistral, the French AI model that basically answered a question in October 2023 on, what goes into your model, and basically this is it's very competitive and everything, so this is basically something we're not going to talk about, and this is, potentially where the true, secret sauce comes from. And on top of this, a lot of the companies are starting to build their own crawlers, their own basically automated bot that is going to go through the internet and basically copy all the text they can get their hands on. So data provenance tools are amazing, very efficient way to properly understand what goes into those models, yet because companies are increasingly closing up and disclosing pretty much nothing about what goes into those models, their usefulness decreased quite quickly over the last year. The second option, the second method, so first I said that I will pause after each method. Everything clear so far? Any questions? Anyone who disagrees? Any lawyers in the room? One? Perfect. Copyright? No. What kind of law? Okay. I have 45 minutes, we have 15 minutes for question. We should talk about what this means. I mean, both for society, but also from an IP and copyright perspective. So method 2 is basically, okay, back in the days, last year, we could just look, and then it was a question of how do we efficiently search terabytes of data. That ship has sailed. Method 2 is basically, okay, can I look at the output of a model? Can I look at the resulting trained model and figure out somehow whether it has seen a specific piece of content during training? Was, 1984 seen by the model during training? And the idea is basically to use something, our idea was basically this is actually a well-known problem in privacy. So privacy of machine learning model actually has been a topic for quite a long time. And actually the gold standard, right, and it started a long, long time ago, like 2000, 2008, some tests were basically developed to see whether aggregates contained information about a single person in DNA data. Can I detect that Mark's DNA data was in an aggregate data set, yes or no? And this is actually called something called membership inference attack. And the goal is basically, by looking at the aggregates, in this case by looking at the resulting trained model, can I figure out whether a specific book was seen during training, yes or no? Traditionally in privacy, the way we do this is something called shadow models. And shadow models basically is a really efficient technique in which basically I take a data set and I sample basically without replacement. And then in half of my data sets, I will put Mark in them. And the other half, I will not put Mark in them. I'm going to train hundreds of models. And then I'm going to train what we call a meta-classifier, so a machine learning model on top of those machine learning models to basically predict which one of the model has seen Mark data and which one has not seen Mark's data. Super efficient, super effective way to test the privacy of machine learning models. Well developed, well used across the privacy literature. Only issue, you know how much it costs to train a large language model? We're going to have a really hard time convincing EPSRC that they need to give us 100 times that so that I can train a 50 model without Mark's data and 50 model with Mark's data. 50 model with 1984, 50 models without 1984. So the idea works, it's really good, but we can't do it. So instead, what people have started to do is basically something called document-level membership inference attack. So instead of creating artificially shadow data sets, model 50 of them have seen Mark's data, 50 of them have not seen Mark's data, I'm going to look at a model, and I'm going to read a piece of text to the model. And by read a piece of text, I'm literally going to give it the book, token by token, and think a little bit of, like, you know, your favorite movie in which someone is on the chair, like taking the, you know, the debunked lie detector, right? And the little thing that says whether you're lying or not after calibration. Think of it as something similar. Basically, we take the model, we put it on the chair, and we read the book to the model, and then we try to see the extent to which the model is surprised. And surprise is basically perplexity, right? It's could, and by surprise, right, the lie detector and everything, technically what it means is just we look at whether the model correctly predicts the next token. Or actually more, and I'll go into the details, where is the correct token, the probability that the model gives to the correct token. Okay? So in 1984, for example, I would start and I would say, you know, war is peace, freedom is, and then I look. And then if the model says totally slavery, then it has probably seen 1984 during training. That's basically the idea. A bunch of methods, actually 2 papers, one by us, one by a team in Washington, actually developed pretty much the same method concurrently. I'll start with ours, which is slightly higher level. It's basically literally we query the model for every single token in the text. Then we do 2 things. The first one is we normalize each probability by dividing it by how rare a token is. So basically, if the correct token is a very popular token, it's an and, or it's like, you know, something really simple, something that appears in the English vocabulary very often, we give it slightly less weight versus something that is more surprising. We just normalize the token. And then on top of this, we basically train a machine learning model on the output of every single token, and we try to get the model to tell us where should we look. What is a good signal that a specific piece of text was seen during training? And to train our model, basically we went back and we're like, okay, the model has been released on a specific day. What I'm going to do is I will take text that I know pretty much for sure was seen during the model during training, right? Typically command crawl. And then I will take the exact same, as close as it gets, text released right after the model was released, which by definition, chronologically, the model could not have seen this during training. And I'm going to train a model to see the difference between the two. And basically what we see, And basically what we see here, this doesn't really work. Yeah, basically what you see here with the AUC is that it works pretty well at detecting which book were seen during training. We have an AUC of 86 for books, which are fairly long piece of text where we have quite a lot of cues. The other method released, I think we posted our paper, and then a week later they posted their paper, so really concurrent work. They propose a very similar method. Instead, they do two things differently. First, they decide to focus on the lowest of the probabilities, which basically means they focus on when is the model incorrect. So war is peace, freedom is, and if the model says very low probability for slavery, then it probably means it has not seen 1984 during training. So they really focus on low probabilities, and instead of a meta-classifier, they just decide based on a threshold. They average and they decide on a threshold. And similarly, they focus on Wikipedia and they get an AUC of 76. So two fairly good concurrent methods post hoc, taking a trained model, reading the book to it, and try to see the extent to which you can predict whether it has seen this piece of content during training. And then another method that came out, I think a few months later, that basically builds upon the first one and basically propose a different normalizing factor to further improve the result by 7 percentage points. All very good, super useful. Big, big limitation, though, is basically from a copyright perspective, what is difficult is, war is peace, freedom is. I can input this to my model. But the fact that the model would correctly give a very high probability to slavery does not necessarily mean that it has seen the actual 1984 book. It might have seen, war is peace, freedom is slavery, has been copied all over the internet. Blogs, fan fiction, Wikipedia page for 1984, et cetera, et cetera. So it can actually, what's really difficult here is like where did the model learn this from? And can I definitely conclude that it learned that specific piece of knowledge from the original source, which is, in this case, the 1984 book. And also, a bit worrisome from a scientific perspective is that all of this is post hoc, right? We talked about it, right? It's basically in privacy, we create this perfect setup in which 50 models, by definition, have seen Mark's data because I put Mark's data in the training set for those models. And for 50 of them, they have not seen Mark's data because I did not put Mark's data in them. Here, all of it is post hoc. We have this really complex billion parameter machine, and we try our best to get the model to confess. And the issue is that this is actually a very difficult task, and they have been concerned being raised on something called distribution shift. Basically, the extent to which we are truly capturing the fact that it has seen this content, as opposed to the model learned that between the one published slightly after the release of the model and slightly before the release of the model, there is something that is different. But something that is different maybe isn't actually what you're interested in. Maybe it's not actually about seeing the content. And this is very much exemplified by a picture that we have in the paper, in which basically between members and non-members, right, books that were seen by the model and books that were not seen by the model, and you look at the publication date. We got those from Project Gutenberg. And basically, the issue we identified is that the members, the ones seen by the model, are shifted to the left. They're shifted towards older books. And obviously, any one of you, if I give you a book written in English from 1850, it will be trivial for you to tell me that this is a book published last year versus a book published in 1850. And this ever slight distribution shift maybe means that what the model actually learns is that this is an old book versus a new book, not that it has been seen during training or not seen during training. So it would be really useful. The issue is, at this point, a year later, we do have some concerns on, basically both the scientific validity and what a positive result would mean coming out of those methods. Any questions on those before I move to method 3? Please.
So the novelty of an author lies not in the sentence level, but at the concept level and all the sentences. Would that still be there?
So here, it's literally the entire book. So we literally, it's you go through the book, and literally you look at whether the model is surprised, right? Like, does the model correctly predict the next word in your sentence? So there is nothing, it's all a meta-classifier, right? So it doesn't aim, the min-k, for example, was making some assumptions. For example, that you learn the most when the model is wrong, right? If the model cannot tell me that freedom is slavery, then it probably means that it has not seen 1984, because that sentence is just, that's the big brother thing, right? It's repeated across the book a number of times, and you would expect an LLM to have learned this. Otherwise, it's basically, can I make a prediction? And the issue is, we can make predictions, but first, we're not really sure that we're predicting the right thing. And second, even if the prediction was correct, we cannot guarantee that the provenance, that this is where you learned this piece of information. So this would be the go-to, and this is where a lot of people went, including us. I think a year later, and handful of papers later, I think we realized that it's useful, it gives you a first hint, but it has some strong limitations.
So maybe I can ask my question slightly differently. What's the level at which uniqueness must exist for it to be identified? Because in freedom is slavery, it's a very unique phrase, right? It's a catchphrase in the book. But other authors have uniqueness at more abstract levels. What happens then?
We tried. So basically, we don't know. What I can tell you is that 85% of the time, I can tell you whether a book has been seen during training. Where does it come from? The explainability, as often with machine learning, is like, it is really difficult. We did spend some time on this. We do have some idea, but it's really, really tricky to answer. Because it's about, it's an LLM, right? It's about the whole context and one prediction. And then you need to move the context, see, and have, causality, etc., to truly be, okay, this is why. So war is peace, freedom is slavery is just an example. So this is method 3, and yeah, this is the slide that basically says we do have some concerns. Method 3, which I think actually is the most exciting one at the moment, is something that we call copyright traps. And this is actually a new take on an old idea. Back in the days, people were actually inserting fictitious entries into maps and dictionaries to prove that their content was stolen. Because your dictionary looks like my dictionary. Your map of London looks like my map of London. Well, duh, it's a map of London. If they were to look very different, we would be worried. And so basically what they were doing is they were actually inserting, and this is my favorite one, fictitious ski slopes in the middle of London in one of the parks. Or there were fictitious entries, a Mount Weasel, which is a fictitious entry in a dictionary. And then if I were to include my ski slope, and then when I look at UMAP and UMAP has a ski slope, I think this is Agerton Park, then I know that you probably stole my content. And the goal was to say, okay, can we actually do the same thing when it comes to large language models? Can I include fake content and make the model remember it? And more specifically, what we're doing here is we generate fake sentences, completely synthetic sentences that are very likely to be unique. And I generate 100 of them. Who knows about randomized controlled trials in medicine, right? Placebo and drugs. Basically, we do the same thing. We generate 100 sentences. I randomly select one. I insert one into the training data set, and I keep 99 on the side. Never seen by the model. I train the model, I put it on my website and everything, then I look at models, and similarly, I look at perplexity. I look at the probability the model gives to that sentence, and what I do is I actually compare the probability that it gives to the trap, the fictitious entry that was inserted in the content versus the 99 that have never been seen by anyone. And using this, I try to detect whether a piece of content was seen during training or not. So basically here, I take my original content, I add synthetic sentences in it, and then I look at what the model says about that sentence versus the 99 generated in the exact same manner, but never seen by definition by the model, by construction. And basically what we show is that, so this is how we generate them. So basically we actually use a reference model. So we use a model to generate super unique data. Basically we use a model and we're like, okay, please generate sentences that you would give a very low probability to, so that we're really, really sure that those sentences both will not exist anywhere else. And second, because they are so weird, they're more likely to be memorized by the model. And then basically what we show is that, and then we have a randomized control setup in which again, the sentences included, we keep other ones on the side, and then 3 basically attacks, 3 ways for us to perform the statistical test, basically, to see whether a sequence was seen by the model or not. And basically what we show is that, so we actually inserted this. This is not like, this is not like a small scale study. We actually partner with a team in France who developed, believe it or not, a model called Croissant LLM, which is an English, French-speaking model that they called, originally joking about calling it Croissant, and then it picked up and they ended up calling it Croissant. And they actually let us, so this model is a 1.3 billion parameter model trained on 3 trillion tokens. And we inserted our traps, our synthetically generated sentences in a bunch of random places in their training data set. And then we looked at whether we could detect if the sentence was seen during training or not. And basically what you can see is that the sentences are repeated and they're randomly spread across the data set. And basically what you see here, the green curve, the blue one, and the red one, and this is for a sequence of 25 token, 50 token, 100 token, you can see that the more the sequence is seen, the more the model remembers it. Basically, this is exactly what we expect working. We just keep repeating the sentence. We keep telling the model the same specific sentence. And as the model sees it more and more, basically it remembers it more and more. And we end up, when you look at the green, right, with a fairly good detectability after, so this is the total training of the model for the sentences. So basically was, what is it, like 60, probably 68 AUC, take it as accuracy to keep things simple. Basically, we manage, the model exactly behaves like we expect and just memorize the very weird sentence that we keep repeating to it. And I think this is for 100 repetition. So basically, we repeat the same sentence 100 times, and that's sufficient to get out of 3 trillionth token to get a 1.3 billion parameter model to remember that specific sentence in a way that we can then just look at the model and detect it. Very quickly, before I take questions, so this leads to really accurate document level membership inference, right? Because now I know exactly where I inserted my traps, and I look at whether those traps have been seen by the model. Potentially, I can even tell you how often the traps were seen by the model. And I can also tell you that the weirder the sentences are, the more likely they are to be memorized, which is great. More unique, weirder, absolutely not English-sounding sentences are amazing. They throw the model off. The model reads a text, something, and then gets to a really weird sentence that makes no sense. That will actually push the model in all the wrong ways, and it will make it remember. And basically what you can see here is that the weirder the sentence on average, the more memorized they are. Oops. Oh, yeah, here it is. This is just a conclusion, and then I think we can discuss, what it means, both copyright, what it means for memorization, what it means for, how model learn. But basically, we think that transparency is essential, right? Those models will have a dramatic impact. They are already used across the board. They will impact everyone's life. Understanding what, and more importantly, where they learn from, is, we think, extremely important. 3 methods. One of them, basically efficient search, relies on companies being open and transparent about what they use for training, which unfortunately is not the way we're going. Post hoc is the most convenient method, right? It's literally, you can take a model and be like, have you seen this? Have you seen this? Have you seen this? Have you seen this? Lots of excitement. By now, I think we're a little worried of the results. We're a little worried of, okay, how strong or reliable are the results that we're seeing. And then method 3, traps. Basically, randomized control. What we've learned, maybe we need to relearn. What we've learned in medicine for a long time, which is the only way to actually get causality, the only way to do good science, is basically to do randomized control and to give placebo to half of the people and the actual drug to the other half. Maybe we need to do the same thing when it comes to large language models. We need to give them a few things, keep other ones that are exactly the same, but just not given to the model, to truly understand how they learn, memorize, and ultimately be able to detect that specific content was used, is, we think, the most effective method we have today to understand whether a piece of content was seen during training by a model, and try to get a sense of how they learn and how they memorize. And I think that's pretty much what I wanted to tell you. And I'm happy to take any questions you might have. I've seen a few hands, so.
Can I ask one? So I'm thinking about Phoenicia's question, and your AUC for the last method, you got to 70 for the 100-sentence exposures. And I'm wondering if that tells you something about the question that, you could get to 86 if you're using a book. You could get to 70 on 100 words, and presumably there would be an interaction between that and the weirdness, as you said. So I think that starts to sort of answer the question a little bit.
It's basically, think about it, right? It seems a lot, right? It's 100, right? But it's 100 by 100. How much is 100 by 100? It's 10,000. And it's basically 10,000 tokens out of 1.3 trillion. So it is already pretty good when you put it in perspective compared to everything else the model has seen. Whether that can go up, I think we've shown that it can go up by repeat more, and it will go up. As you can see, right, it's very nicely linear. Repeat it more, it's going to be memorized more. Give it longer sentences, it's going to be memorized more. And then make sentences weirder, and it's going to memorize more. But yes, this is, we think, beyond the whole provenance and copyright question, we think a really great tool to start to understand, knowledge acquisition by LLMs, if you will, and or, memorization near generalization question, which is like, what does it, how does this back propagation at token level actually lead to the model remembering and then remembering at first and then generalizing later on. But even state-of-the-art model, I guess everyone has seen the New York Times lawsuit, right? And the regurgitation, the fact that the model pretty much gives you a verbatim copy of an article by the New York Times. That is, to me, either you can give it task, and this is what a lot of people do, which is like, oh, like the LLM is better than, third year's law student at Georgetown to take the bar or something. The other side is basically, okay, at a fact level, like how much does it generalize, right? Learn like you and I, like my daughter, and to which extent does it actually has seen all of the internet? And so basically there is always something that looks similar enough. And it's probably somewhere in the middle. But it's really two ways to, different ways to try to understand knowledge acquisition by LLMs.
Oh, I'm in the statistics section of Maths Department at Imperial. My name is Arvind. I think the problem that you're considering is maybe attacked in a different fashion. Could you not simply mix up, say, books by 5 different authors at the same time, and then see if the particular, let's say, artificial intelligence is able to distinguish between them, because they are mixed in a random fashion, or is it already been done?
Sorry, I'm not...
Say you take a detective story. There are 5, 6 similar authors. You just mix them up yourself and see, instead of a training sample, you use that as your test bed.
So are you suggesting that I give it a book or I don't give it a book and I see whether it makes a difference?
Yeah, that's right. Simply combine in a random fashion similar books and see if the particular program is able to detect them.
I mean, we could. The issue is basically training one of those state-of-the-art models cost a couple of million. And so if we can convince CPSRC to give us 10 or 100 times a couple of million to train 100 models, we could do this. But because, and we can't, and basically, and I'm saying this jokingly, it's just basically it's really, really hard because we know that some of the behavior comes with scaling, right? So the scaling laws are actually where a lot of what people call, I don't like the term, but emergent capabilities comes from the scale. And so you can try to study things on toy models at small scale, but the extent to which, can I take a model, this is 1 trillion tokens and 1 billion parameter. Can I decrease everything by, 3 orders of magnitude and then train 100 of them and then make claims on this that will be true in the trillion token billion parameters? We know that the scaling laws are very much nonlinear. So that's why it's really, really hard to have. That's what we do in privacy. We have shadow models. Literally, we do what you suggest, right? We just train a bunch of models and we compare. The issue is here, the capabilities are coming with scale, which basically means that unless we can do scale 100 times, we can't, or you have to trust the toy models and the extent to which the toy model generalize to the big one. And sometimes they do, sometimes they don't. But that's really where the challenges are.
I think you're saying it's not feasible.
I mean, it is it's all a question of budget. It is absolutely feasible, but it's
Thank you. Yeah, quick question for me. So I'm interested in how you can see this transferring in a practical sense into the world of copyright protection and infringement. So if you are an author, using your book analogy there, do you envisage a scenario with lots of random sentences written in invisible ink that only the LLM would read throughout a book, so it doesn't interfere with the experience of the reader?
No.
I mean, how do you see it transferring in a practical sense?
Basically, so we actually tried, and we tried to see, okay, can we take sentences from the book, and can we you know, my original idea was basically, can I take, you know, can I get every book to have war is peace, freedom is something, but slightly more boring, so that it would not be copied over the internet. So something like, I don't know how you guys read book, but when I read a book, like every time there's a long description of something, some people love that. I'm just skipping, right? I just skip. It's like, so they went to the Shire, and then you could see like the sun was really bright, and like I basically skip. I go to like, okay, where does it continue? Basically, could we have this, right? Could we have a bunch of long descriptions that are repeated across the book in a way that people like me will just skip, others will be, oh, it's beautiful, it's part of this something, and then get that to be memorized. The issue is actually this is way too in context. And actually, in context doesn't work. You need to take the model, you need to push it completely outside of its comfort zone to get it to memorize. The model needs to be surprised, you know, when it gets to this. And so actually, in context doesn't really work super well. So you need something really weird. So the way we envision it is mostly digital, right? Which is basically imagine the hundreds of different ways in which on any website, I can basically get a machine to see something and you to not see it, right? And you can imagine white text on white background, that's, you know, 101, and then the hundreds of ways in which I can make things appear and disappear, and the machine is going to see it, but you're not going to see it. And we think there's a really broad range of techniques that one can use to insert this, including even visible one, which is like, hey, like, you know, you go on the BBC website, and the same way that you have a CAPTCHA or something, there's a little thing which is like, oh, this is the unique sentence associated to, you know, with our travel section. It's aimed to protect our content from scrapers. You know, click here if you want to know more. It's another option. But yeah, they're weird. Like you can't. My goal was these long description. It did not work.
I think you've just answered my question, which was pretty much the same. I was wondering about the practical effects on human readers of a text that has been written. And you know, do you? I mean, you know, we've all read pieces where there are some bits that look like nonsense. James Joyce, the most extreme postmodern social science, for example. But you know, would you put in a parenthetical statement to the human reader? You know, this is here just for the purposes of, you know, blah, 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 ignore it. So
it could very
you've
like,
already answered it.
Yeah, that's very much like, it's one or the other. We don't know, like, you know, we don't know yet, you know, what people would prefer in a sense. It's like, you know, like very specifically, this is what it is, right? This is the, I don't know, this is the watermark. This is the unique, like, you know, ID of this content in some way or form, or is it just it's hidden? You don't see it, but it's visible to all of the scrapers.
So you talked about your research, and I think it was very, very interesting, and it's fairly specific around privacy and identifying sources for machine learning. But then when you talk about it, it becomes clear that you think about this in a much broader context, like knowledge acquisition, originality, you call it weirdness. I think creativity would also be in that bracket. So I'm wondering, you know, what sort of adjacent research topics are in that area or adjacent to your area that would take us more and more in the direction of understanding, you know, what makes these machines tick, and what creates knowledge rather than just generates output?
There's a lot. It's really, I mean, that's why, again, I started my research career actually by doing my master thesis at the Santa Fe Institute, which is a small complex system research institute in New Mexico. Basically a bunch of people from Los Alamos that got tired of theoretical physics and nuclear research and then decided to study and found kind of the field of complex system. I think, those LLMs are complex systems, right? They're like the human body. It's like, in a sense, they're, I think it's way like billions of parameters, like, super expensive. We can't just run 100,000 of them and see change small things. So basically, we need to study them in the same ways. And I think, the same way that, we do have, if you take medicine, for example, right, you have the post-hoc analysis, right? Like, this tends to work, or correlationally people who did X and Y, et cetera. And on the other side, you have the randomized controlled trial, right? In which you take people and then, you go to great length, right? It's like you want to study acupuncture, right? And you're going to have fake needles that basically just go deep enough in your skin for you to think that there is a needle in your skin, but there isn't. And basically you use both to try to understand. But no, the gap is huge, but you use both to try to understand how the human body, how a complex system functions. And so we think that this is one of the two ways to understand, those models. And, are they gigantic, compression of all of the internet, very efficiently compressed, that it basically knows so much about that there's always something relevant that it can tell you, to, like they've actually learned and fully generalized, and it's probably neither of those, and it's somewhere in the middle. But this was like one of the ways. The other one is basically what can it do? But again, this is plagued by a lot of the, it's very useful, probably the most directly useful, but pretty much the same thing than post-hoc research in medicine, right? It's really hard to get causality versus methods like this that are much lower level, but potentially cleaner from a stats perspective. If that more or less answers your question.
Hi. My name is André Nogueira. I work for a bank, and these topics here are quite important to us. When using small language models internally, we tend to, like you do with food labeling regulations, right? We tend to go and say, we use this, and that. When you buy food and you go in a supermarket and you buy a hamburger and it's actually horse meat, you should be punished or something like that. Same thing should be like this, right? If you have enough transparency and disclosure, what sources you've trained your data and you put, I've used inflammatory propaganda to train my model. Then you should disclose so that people know that the kind of results you're going to get might include some of that. So I think this is one case where some sort of regulation, could help. A lot of expensive, imperfect solutions where you always have the dog chase the tail type of situation. But I would like to hear your opinion about this type of thing. And by the way, Santa Fe Institute, is that Melanie Mitchell is there?
Which one?
Santa Fe Institute. You mentioned Santa Fe. Is that
Melanie Mitchell, Don Farmer, and others. A lot of complex systems started a while ago there. So small world. You could, if you can pass something through the Commons and the Lords and get companies to behave, you could force every single company to disclose exactly what goes into their training. So at least in Great Britain, I don't think that's the way it's going. I think Europe tried when they actually passed the AI Act, which is the regulation of artificial intelligence, which just passed the trialogue and has been signed into law. There is a section that mandates for foundation models some level of disclosure of what goes into the training. The question is like, how is it going to be implemented, right? Because disclosure, it can be your food label, which is my model is 58% use and 25% patent and something, or it can be, a long list of all the URLs that my scraper used, and it's probably going to be somewhere in the middle. So there are some legislative attempts at bringing some transparency, but again, it's going to take time. we'll see what the AI office decides as the proper level of transparency.
My name is Zulfikar. I'm from technical architect from Metropolitan Police. Many companies use code generators like Amazon Q to generate code or review code. Would it be possible to trace or track code from where it is coming from? I'm not worried about loops or case statements, but concepts, even infrastructure as code, so it can reproduce those things or cryptographic algorithm implementations.
So if you look at the traps, technically you could, traps could be a comment in your code. And that would actually be, to your point, which is like, oh, this is actually comments is a very effective way to get, if it doesn't get removed, to get a model to, learn something without this having any impact on utility, because comments are ignored when code is executed. So you could imagine doing this.
Perhaps yes, but no criminal is going to come back and tell us that we found your trap, or another state actor it's not a copyright case. It is basically somebody else who is organized crime or some.
Oh, if you want to attribute who wrote a specific piece of code. I know very little about this. All I know about this is that it's, at least what I've been told, is that it's a very difficult task.
I'm an academic working at Manchester Metropolitan University, and the area where I'm in, is in fashion. And as you know, it's a prolific amount of data, prolific amount of imagery, etc., and it's copied right around the world. And if you obviously you'll know Shen and how it's managed to scrape and get all the data off. So when you're working in a regulated environment like what ChatGPT and Gemini are within, that's fine. But as the technology goes outside the regulation that we're all used to, this is very hard to, the copyright laws sit outside our regulation, and yet it's accessible to everybody. Do you know what I mean? At what the volume of data, and also the nature of geopolitics also is really challenging. Has anyone sort of considered that at all?
I mean, copyright law is this fascinating thing. I mean, basically, so take, there's what, like 4 models, right? There's the US, UK, Europe, and then a lot of countries that have decided that there's no copyright law. So I'll start with the easiest, which is like Singapore, Israel, and others. They're like, okay, there is no copyright law, right? Just come and train your models, and no copyright law applies to trained machine learning models. It basically takes the text and data mining exemption, and basically everything is fair. Then you have the US, which is like, oh, is it fair use or not? And the courts are deciding on this at the moment. There is Europe that says, it's fair, it's okay, but people need to have a right to opt out, which you do need to respect. And then you have the UK, which basically Brexit happened before copyright law, the update of copyright law happened in Europe, and they've been, basically they've been trying to update it, but, generative AI was a thing by then, and by now it seems to be extremely difficult for any update to happen, because suddenly, billion valuations, content, creative industry, it's like, they're trying, but it's really difficult. And then all of the question, which is what happens, right? Because back in the days, right, is like, sure, you can go and you can copy a book in Singapore, but you cannot ship it back to England. What about models, right? Can I take content from UK, train it in Singapore, and ship the model back? Can the output, basically there's 2 things, which is first, if the output looks too much like copyrighted content, then you cannot use it in the UK, so you're stuck with your model in Singapore. or even if the model is proven to contain somehow enough of a copy of copyrighted content, then the model is equivalent to a book and you cannot ship the model back to England. Maybe you can query the model in Singapore and get the results back to England if the results are not copyrighted, but fundamentally no one knows. It's basically the input, you use copyrighted content as input. Copy, does the model somehow contain a copy of copyrighted content somewhere hidden in the parameters? And then the output, is the output fair use and or too close to copyrighted content? And these are basically the three questions that we're wrestling with technically at the moment. But it's fascinating.
I think we have time for the final, one final questions.
You're the master of ceremony, Kai.
I do the shortest path.
In the Euclidean space.
What I see is that there's huge amount of startup AI technology companies right now. Every day you hear about new companies in X or Y area. But with a lot of startup companies, they don't have their own data. It's like any other company. So in order to get that data, either they have a choice of partnering with a big company, and at the start, a big company probably might not be investing or not want to invest in them. And so the other choice they have is to look for data available in their market or wherever. And I see no way but for them, in order for them to move forward, they have to take that risk of copying some kind of data that's available in the market. Like big company like ChatGPT, which exactly copied New York Times. So is there a way out for a lot of these new startup companies, rather than getting big companies to essentially give the data for free?
I mean, there's a lot of different takes that people have on what is, on the one hand, we want the technology. On the other, newspaper and the news industry is extremely important, and people who generate original reporting and content should be compensated fairly for the use of their content and what the content provides to large language models. So, the answer is probably somewhere in the middle. And then back in the days, right, that's like, in the US, fair use was the, where they set the threshold. The EU set a different threshold, which is a bit more market friendly, which is basically you can opt out, which basically lets content owner to be like, oh, you reader can go to my website, but you model developer cannot use my content, and if you use it, then I can sue you, et cetera, and therefore you need to negotiate with me fair compensation at market value. And then on top of this, you have, and you've seen some of those deals, right? There have been deals between Springer and the Financial Times, I think, and Le Monde, El País. A bunch of companies have been partnering with some of the LLM developers to exchange basically knowledge and or money for content. And so it's basically, where do you think, do we need a collective society, so that small news organization also that don't have the resources of the New York Times to sue someone also should get like, a fair, value for their content? How do we make sure that everyone, that it's fair from a competition perspective, right, between some of the players who are more than happy to dump, a couple of millions onto the BBC to buy content, versus a small innovative startup out of Imperial that does not have 3 million lying around to buy content. Again, these are some of the, as a good academic, I just give you the, kind of the parameters of the equation, and then we collectively as a society should decide, where should it, what's a good sweet spot.
Okay, so let's thank again for Elizon for the very insightful presentation and also for the discussion. Thank you very much.